Okay.
Okay.
So now we are live. So first of all, thanks a lot, Sergey, for being here today, for being part of this cycle, this IOTA Evangelist Network talks. With this, we are trying to cover what you guys at IOTA Foundation are doing. So we already have a Vlad Semenov, we have Darcy Camargo. The idea is to be able to inform to the community what is being done. So I'm going to introduce Sergey. I don't think he needs much introduction, but let's do it. Sergey is a mathematician, as you guys know. He's a research mathematician, and he's working in the field of probability theory and stochastics. He's also the IOTA co-founder, one of the IOTA co-founders, and he is the head of the research team on IOTA. So he's driving the research on coordicide. So today's talk is going to be about fast probabilistic consensus. This is a novel protocol that Sergey created, and it's a key feature for the consensus once the coordinator is removed from the network, from the IOTA network. So as usual, guys, we will be using the chat, in this case, the YouTube chat, to send questions. And once Sergey finishes his presentation, I'm gonna be doing the questions one by one. Okay. So I think that's all. Let me. Okay. And whenever you want, Sergey, you're good to go.
Okay.
Okay.
So thank you very much, Karpincho, for inviting me, and thank you very much, everybody who came to see this talk. So I'm going to talk about. I'm going to tell you about first something about probability. General probability. So these coins here are just coins that you toss and obtain heads or tails. Walks are random walks. And then I explain about the relationship of all that with fast probabilistic consensus and related models. Okay, let's start. Just a warm up for you. Imagine the following situation. There are 1,001 people who have coins with heads and tails with them, and they would toss these coins and report their results. So in principle, these are fair coins in the sense that it comes heads with probability 1/2, and it comes tails with probability 1/2. Now, these are a lot of people, of course, and some of them are kind of cheaters, and they understand that nobody will really verify what they report. So they want to collude and always report heads to make heads win. Win in the sense that there will be more heads in the outcomes than tails. That is at least 501 heads. Problem. What is the minimal size n of the colluding group so that the heads wins with probability at least 75%, 3/4? Okay, now I want you to think about it a little bit and just listen to your intuition. Ask your intuition what it tells to you. Should n be small, like at most 15? Should n be between 15 and 26, or between 27 and 39, and so on? Or should n be greater than 100 or greater than 200? So what is the minimal size of the colluding group? So now I will give you some a minute, 30 seconds, just to think about it and see what you choose. Let me close the door here in the meanwhile. Okay. Just a bit more time. So what do you think? How large this n should be? How much corrupt people from 1001 are necessary to really bias the result? Okay, good. Now here is the answer. You need only 22 colluding people. And then you can calculate that in this situation, heads wins with probability approximately 0.759. Yeah, so normally people kind of tend to overestimate this this size. So that's a little bit of not really intuitive example of how it is easy to bias the outcome in this balanced situation. Okay, now let me describe something which is called simple random walk in dimension 1. So imagine this, you can imagine those same people who are tossing coins and reporting their results, or you can imagine just one person who is tossing a fair coin, which gives heads or tails with probabilities 1/2, 1/2. But then what will happen, we will kind of construct a trajectory out of this. So first, you toss a coin and the result is heads. Then you make a kind of step up. So the horizontal axis is time. The vertical axis is just the position of the walk. Each time when you obtain heads, the walk will go up. Each time you obtain tails, the walk will go down. So you obtain heads, then you have tails, and the walks goes down, then it goes down, then up again, then up, up, down, and so on. So it just, let me show it once again. It goes like this. And so on and so forth. So this is a very simple example of what we call a stochastic process, or Markov chain. However, this very simple model is very interesting and surprisingly rich. I will give you a couple of, let's say, strange or surprising facts about it. First of all, let's consider this trajectory of simple random walk of these outcomes from accumulated outcomes from coin tossing up to time 2n. And we can consider this t, capital T, which is the so-called time above zero. So it's here the trajectory is above zero, here also. So this length plus this length is what we call t, the time above zero. You can think about like two players are playing games. They toss a coin. If heads, then the first player wins $1, and so second one pays $1 to the first one, and if tails, then the first one pays $1 to the second one. And then, well, initially they had equal capitals, but then at each time moment, the height here would be the gain of the first player. So this t can be interpreted as the time when the first player was leading the game, was ahead in the game. Okay, now let's consider another quantity, another random variable, as we say. Let's call it z. So basically z is the last time those two players were equal. So it's the last draw, that last moment, and they were drawn, and then after this moment one is leading till the end. Yeah. Okay, so again we have this time above zero until to n, and we have the this last zero of the trajectory. How they are related? Apparently there is no relationship between them whatsoever. However, it turns out that these quantities are actually the same, in the sense that they have the same probabilistic distribution. So the probability that the first player was ahead during time 10 is exactly the same as the probability that the last zero was at time 10. Yeah. Moreover, let me go back a little bit to this picture. Intuitively, when you think about this trajectory, you think that, okay, it will go down, then go up, then go down, then go up, then go down, then go up. It will kind of oscillate like this, right? So it should be kind of more probable that the first player was leading like half of the time and the second player was leading half of the time. Well, however, it turns out not to be the case. It turns out to be exactly the opposite. So I'm now going to show you the so-called arcsine law. And before this, I would like to show you the graph of this function. F of x is 1 over pi square root of x minus x. So it's function like this. It attains its minimum in 1/2, and it has it goes to infinity here in 0 and here in 1, but still you can show that it is a density, in the sense that if you integrate it from 0 to 1, it gives you 1. So it can be used as a density of a random variable. And then it turns out that both these variables z and t, if you divide by the final time to n, they have approximately this density. So yeah, the indefinite integral is just this arcsine of 2 over pi arcsine of square root of x, and that's why this is called the arcsine low. Now, to make it clear that this result is in some sense surprising, very unintuitive, let's consider two players who play this game, tossing a coin once per second during 1 year. So this is a lot of time. You have a lot of seconds in a year. However, it turns out that with probability 20%, which is not at all small, one of them will be leading for less than 9 days. And the whole other time, the other one will be leading. And with probability 2%, approximately 2%, which is again it is small, but not very small, one of them will be leading, will be ahead in the score for less than 2 hours and 10 minutes. And the other one of them will be ahead for almost the whole year. So this is something which is not easy to believe at first. Okay, this was one surprising example from probability. Let me actually present to you another one. So these things here are the so-called integer lattices. So this one here is called Z, which are the integer numbers. You may wonder why Z, because it's the first letter of a German word for numbers, Zahlen. So this is the one-dimensional lattice of integer numbers. This one here is two-dimensional lattice. This one here is well, what I could draw for three-dimensional lattice. And actually, mathematicians have no problem in defining this sort of thing in any dimension, right? But let's just think about these three. And just as the simple random walk in one dimension that we just considered, from each point you go up or to the right with probability 1/2 and or to the left with probability 1/2, you can actually consider the same sort of process in dimensions 2 and 3. So from this point you will go here, 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 or here with probabilities 1/4, 1/4, 1/4, 1/4, and yeah, the same here. In dimension 3 you have 6 neighbors in particular. In dimension 2 you have 4. So in dimension D you have 2D neighbors. So you just jump to your random neighbor with equal probabilities, which are 1/2D. Now, the basic question that one may ask about random walks is the question of recurrence or transience. So we say that the random walk is recurrent when it just keeps returning to the same position. So if I start from here, then I will go there, but then return, then we'll go there, then return again, and so on. And in dimension 2, maybe I will do the same, maybe not. In dimension 3, it's also a good question. If I start from here and start walking, will I return? Will I surely return to this point or not? You know, it's a natural question to ask, and the answer to this question was given by Hungarian mathematician Polya in the beginning of the 20th century, and it asserts that simple random walk in dimension d is recurrent for d equals 1 and 2, and it is transient for higher dimensions. That is, in dimension 1 and 2, the walker will always return to its starting point once, but if it surely does this, then it will return again and again, so it will just do it infinitely many times. But in higher dimensions, eventually the random walk will just go away. There is a famous interpretation of this remarkable fact. It is attributed to a great mathematician, Shizuo Kakutani, who is well known for many great results, not only this one. For example, this Nash equilibrium thing relies heavily on a theorem by Kakutani. A drunken man always returns home, which corresponds to recurrence of the simple random walk in 2 dimensions, but a drunken bird will eventually be lost. So if you think about this as a map of, let's say, Manhattan, so if you live here and get drunk and go walking like this in a random fashion, then eventually you will return home. But if you are a bird and you do it in 3 dimensions, then you will be not so lucky. Some moment you will just be lost forever. And that may explain why birds do not drink vodka. So this is a mathematical fact, but now we will see a couple of examples which show that the life of the drunken man is not so easy either. It may take him quite some time to return home. So in this quarantine times, it's something to consider. You should not drink too much. Still, examples. So consider this simple random walk in dimension 2. And suppose that you are walking on a plane on a 2-dimensional lattice, and the size of the edge of this lattice is 1 meter. Then, what are the probabilities of first going out of Paris? That is, you start somewhere in the center of Paris, like Pyramide du Louvre, and you do this random walk in 2 dimensions, and you want to know the probability that you will come to Boulevard Périphérique before returning to your starting location. And you can also ask what about going out of our galaxy, of our Milky Way galaxy, if you walk on the so-called galactic plane. You know that the galaxy is kind of almost 2-dimensional, is somehow a pancake or something. So you can define something that you call galactic plane. Actually, there is a giant black hole in the center of it, but let's just ignore this and consider the mathematical aspect of this question. So, you may think that since it is mathematically proven that 2-dimensional simple random walk is recurrent, then you should return, and Paris is big and the galaxy is much, much larger. then you might think that you should return to your starting location before going out of these places with probability very, very close to 1. So the probability of going out should be very, very close to 0. Well, here is the answer. Actually, probability of going out of Paris is around 15%, which is not at all small. And the probability of going out of our galaxy is still not very small, is a bit more than 3%. So you see that our drunken man can really need a lot of time to come home, unfortunately. So here I find I do some publicity for my new book, which will be published by Cambridge University Press. It's about random walks and, well, many interesting things. It's not really cryptocurrency related, but still quite interesting, I hope. And yeah, so these were some examples of facts which are strange, surprising, which show that you cannot always trust your intuition when it comes to probability. Well, you can trust my intuition, but anyway. So now let's go a little bit back to one dimension. We will consider now more general random walks, not 1/2, but like some probability of going to the right and some probability of going to the left, which can differ from one place to another. Well, why do they do this? Basically because this is a very important model which helps us to study some systems, some systems which have real world applications. You can study them through random walks. Okay, so I'm going to explain you some sort of intuition. So you can, I mentioned that you can think about a random walk as a motion of a drunken person, of drunkard. Sometimes in textbooks they even call random walks as drunkard walks. And this symmetric simple random walk with 1/2 to the left, 1/2 to the right can be seen as a walk of a drunken person, which is this circle here, just on a straight landscape like this. So this you have this line which is completely horizontal, and this drunken person will kind of oscillate 1/2 to the left, 1/2 to the right, randomly. Okay. Now, what happens if you consider something more, something different? So let's say this drunken person goes to the left with probability 1/3 and to the right with probability 2/3. So it has kind of drift to the right in this case. Well, you can think about it as a walk of a drunken guy here. on this in this situation, So if this drunken guy is here, then it will kind of drift to the right. I would. I know that this webcam doesn't capture too much, but otherwise I would kind of show you how it goes. But still, you can imagine, I think. So this is a kind of very useful way to bring a physical intuition into this. So let me stress it again. It's not like you had a ball which would go down here, because the ball would kind of accelerate, and the random walk will go with constant speed. So you rather think about this as a drunken guy who will have the tendency to go there, but can still occasionally step to the left as well. And then you can use this this kind of intuition for more complicated pictures. So, for instance, suppose that when this guy is here in this left half of the picture, it has tendency to go to the right, but when he is here, he has tendency to go to the left, and then you can visualize it like this. So here it will drift to the left. Here it will drift to the right. So this drunken guy will drift to the bottom of this picture. And this is another situation, kind of a contrary situation. Here you have drift to this direction, to the left, and here you have drift to the right. And then if it's here, it will kind of have a tendency to go farther and farther from the center, and from here it will go to the right. So, it's a good way to think about walks without looking really on transition probabilities, but rather you just imagine a drunken guy who is walking on this mountain, on this valley. So it has some physical meaning. It's you can think about this as actually potential energy of the system, and I will not elaborate, but it has some good physical meaning. Yeah. So now the moral of the story is that we can just draw something and think about the drunken guy who walks there. Now, let me explain one very important phenomenon in physics, which is called metastability. So, what is metastability? Just think about this drunken guy who is walking in this landscape. So what will happen? So first he's here, and he will tend to go down like this. So he was here, then he will come here to the bottom, and then he will start fluctuating around. We'll go a bit here, but then come back. We'll go a bit here, but then come back, and we'll repeat this for a lot of time. And actually, it's possible to, from some physical and probabilistical calculations, you can more or less know for how much time it will walk there. So this time will be around exponential of this height, or of this depth. We usually call we usually call this thing here a potential well, and this h1 is its depth. and the time which is spent, the drunken guy will spend here, is actually some random constant, well, which is almost exponentially distributed, in fact, but times this exponential of depth. Okay, but eventually the drunken guy will go here. And then what will happen, he will happily go down to this potential well. And what will happen then, he will spend a lot of time trying to get out of here. Yeah. So this phenomenon of spending a lot of time in such places is called metastability. So yeah, then as I explained, it will need like random constant times exponential of this depth to finally go out and to go to the global minimum of the potential. So you can call these like places here and here metastable. So these are places which are not really the global minimum of potential, where the drunken guy will spend really the majority of time. So this is called stable state. Well, you can say that it's something that is known in physics as ground state. It's not completely 100% correct, but well, you can call it so if you want. And so these two are metastable states. You will eventually come out of there, but you will spend a lot of time there because exponential is really a lot. Now we are finally coming to something IOTA related. So in IOTA we have this voting mechanism which we use to decide in case of conflict, which we use is used to decide which transaction is valid, which transaction is invalid. And you can think about this in the following way. By the way, it's called majority dynamics or threshold water models in probability. So there is a graph, each side of which has an opinion, 0 or 1. You may think about it as 0 means that some given transaction is invalid, and 1 means it is valid, and the nodes of the graph are the nodes of the network. And at random moments, each side consults or queries, as we call it, some few neighbors of it, and adopts a new opinion using some majority rule. Like if most of those whom I asked have opinion 0, I will also adopt an opinion 0. So I have to say that this is different from those PBFT-like protocols from computer science, which come to consensus, but they really consult almost all other sites, at least a fixed proportion of these sites. Here in these probabilistic water models or majority dynamics models, you consult not a lot of them. Yeah, so this this class of models have many interesting properties. They were introduced in the 70s of the last century, so it's more than 45 years by now. and they were studied really a lot since then. And the property that is particularly interesting for us is that the models of this class only have two so-called extremal invariant measures. I will not explain what does extremal mean. It's some linear algebra and some convex analysis, but anyway, they have two, let's say, important invariant measures, which I also will not explain what is that, but basically, if everybody has opinion 0, then this situation will remain so, and if everybody has opinion 1, this situation also will remain forever, and they are invariant in this sense. And yeah, that is, it's kind of natural to call these all 0 or all 1 states the consensus states. And so now you understand why do we care about this sort of dynamics. Because we want consensus. We want to achieve consensus on the status of each transaction. Okay, now comes this random walk intuition. You can think about the majority dynamics as a random walk on this sort of potential, on this mountain, if you want. And so on the horizontal axis, you have the proportion of the nodes which have opinion 1. And also the height of this mountain is actually infinite. So if this walker comes down to the end, it kind of can never go up again. This reflects the fact that you can never go out of a consensus state for this sort of model. So you see, when the situation is more or less 50-50, this drunken guy will fluctuate around this point, but eventually at some moment he will either go here and fall down to the 0 consensus state, or it will go here and then fall down to the 1 consensus state. Okay, so I hope this is clear, but this is only for the kind of ideal model without Byzantine actors. So here we are assuming that everybody is honest, everybody just honestly reports their opinions. Now, what happens when we have Byzantine actors? So some nodes are actually malicious. They may lie to others about their current opinion. And then it turns out that if the proportion of honest nodes with opinion 1 is large, you still go down like this. If the proportion of honest nodes with opinion 0 is large, you will still go down like this, but yeah, it will not be minus infinity, but some big and absolute value constant, because Byzantine nodes can always say anything to them. But here it's in principle difficult to draw this potential, because this depends on the strategy of these malicious nodes. For example, suppose that they adopt naive strategy. Like they will always help the weakest. If opinion 1 is prevailing, then all the bad guys will vote for 0, thus helping the 0. If the opinion 0 is prevailing, then they switch to 1 and try to help the 1. And it will correspond to this picture here. So this is the help the weakest strategy. Then, so this is the 50-50 situation here in this point. Then the opinion 1 is prevailing a little bit among the honest nodes. The Byzantine actors will create a drift towards the center. If the opinion 0 is prevailing at the moment, then they will create a drift here towards the center. And as we know, they will be able to maintain the process in this undecided state for a lot of time, because this time will be basically exponential of this height, this depth here. And exponential is a function which grows really, really quickly. However, when these Byzantine actors are really malicious, then they want to really break the consensus, like convince some honest nodes about opinion 1 and convince other honest nodes about opinion 0. They can actually think about even more intelligent strategy, which is this one called let's bias it strategy. So instead of just helping the weakest, instead of constructing this potential here, they would rather aim for keeping the drunken guy a bit biased, a bit still in the zone of their control, but such that the opinion 1 has more votes. So in this situation, some honest nodes would be unlucky to think that they should really decide on 1, because they would really get more 1s than 0s as answers to their queries, and by the force of chance, still the attacker can maintain this drunken guy here for a really lot of time. So by the force of chance, some honest nodes can adopt the opinion 1. And then the bad guy would kind of sway this picture to the other side and help the 0s and make the other honest guys to appear to adopt opinion 0, which will cause a fork in the network, which is obviously not good. And yeah, that is what is called the curse of, well, that is what I'm calling the curse of metastability. This is why, in principle, this sort of majority dynamics is not really Byzantine resistant. Now, in FPC, there is an additional device, additional mechanism that help us defeating metastability. So these are these turn-based random thresholds, which are described in this paper by Bill Buchanan and myself, the fast probabilistic consensus paper available in the archive. Basically, the idea is the following: whatever the attacker might do in this region, whatever strategy he chooses here, with uniformly positive probability, like 1/2, 1/3, or I don't know, 1/7 or something, just in one round, the drunken guy will jump out, either here or here. And then the bad guys will not be in control anymore. Then the consensus, the usual majority dynamics will work, and they will, all the honest people will either converge to consensus about 1 or to consensus about 0. So this is the most important thing, that it's important that everybody end up with the same opinion. 0, 1, but it's important to avoid the situation then one honest node decides on one thing and the other honest node decides on another thing. Yeah, so this is the trick that we have in fast probabilistic consensus. We use some external source of random numbers to construct these common random thresholds, which defeat the metastability. And we don't really need a lot from these random number generator. They, for example, if it's a little bit biased, it's still okay for us. Even if the attacker gains control over it from time to time, it's still fine, because eventually the attacker will not be able to predict the next random number, and the network will sway to one of the sides and will end up in the consensus state. So this is the mechanism that we use to defeat metastability and ensure that we will come to the consensus. Well, I guess I'm done. Thank you very much for your attention, and please ask questions.
Okay, so we have some questions. The first one says, I'm going to put the questions on the screen so you can read them.
Okay.
So how would you briefly explain the changes that random walks will have from the current implementation of IOTA to the coordicide protocol, if any changes, right?
Well, I would say that everything will change, because now we have random walks in the protocol, but these are random walks of completely different nature. So now we have these random walks on the tangle, which help us to select tips. And in the coordicide, we will not, in principle, we are not planning to do this sort of random walks anymore. In the coordicide, we kind of only use random walks to gain intuition about what's going on with the voting procedures. So I would say that random walks now and random walks afterwards are like different things, not related to each other.
Okay, not related. So the next question says, on FPC, is there a way to flip a node's vote once the voting process is finished? All rounds are done and the consensus on a given transaction is achieved. So is there a way to?
Okay, so in principle, since the consensus is probabilistic, with some very, very small probability, it might fail. So we, our simulations show that it will hardly happen frequently. It will be a kind of very rare event. But on the very unlikely situation when your node is really, really unlucky and kind of disagrees with the rest of the network. It's possible to show that if a bad thing happens, it will not happen with a lot of nodes at the same time. It will likely happen with only a few of them. And then it's also easy to detect that your node is on the wrong side of the public opinion, because you kind of start seeing that all the things you like, other people dislikes, and vice versa. So in this situation, we have kind of a trigger that indicates to your node that it should kill itself and reset. But again, this is something really unlikely to happen. It will likely happen very rarely with rare individual nodes who will just resync and go back to the consensus. Well, we will test it in Gossamer.
Yeah, but anyway, it doesn't matter, I think, because once the consensus has been achieved, it doesn't matter if the node changes its votes. I mean, it is already computed as whatever he voted originally, right? So it shouldn't matter to change votes that a node did in the past. This is what I think. I don't know if I'm right.
Yeah, I mean, not normally the nodes would not change the votes. So only in a very unlikely situation when kind of your node is on a very, very unlucky day and it goes everything wrong and it has to resync. But you may think of it as just, okay, it can also happen that your computer hangs or someone places a virus in it, so you have to erase some recent history and resync. So we don't expect these resync events to be very frequent. But
Okay.
still, we need to have some emergency situation which allows to the node to go back to the majority.
Okay, so the next question says, what force should cause this gravitation towards a desired direction?
Well, the force of probability. It's something which is called law of large numbers in probability. But let me go back to this picture here for a second. So here, you see my screen, right?
Yeah.
So here, for example, this drunken guy goes to the right. Why? Because for each step, it has twice the probability of going to the right than to go to the left. It chooses the direction to the right 2/3 of the time and direction to the left 1/3 of the time. So this is what forces it to go down. It's not the gravitation really. As I told you, we use these pictures of mountains and valleys just to gain a physical intuition about what's going on, but it's really a matter of probability.
Okay. So the next question says, in coordicide, when a transaction is sent to a network, it must wait for a bit to see if there is another conflicting transaction or not. Is that quarantine? I don't know if that is the term. Yeah, quarantine time variable?
No, we pretend to make it fixed, like I don't know. I don't really remember what is the amount of time we are aiming now. It may be 10 seconds or something, because we want to kind of start from the pre-consensus state already, so that with high probability the majority of nodes would more or less agree on the status of each transaction, and then it will kind of help the voting procedure to work. So it's, how do I say, with some fixed time of order of 10 seconds or so, you may be reasonably sure that in normal circumstances the majority of nodes will receive all transactions issued 10 seconds ago.
Okay, so it's a fixed number. It is not variable.
Yeah, but we will test this in Go Shimmer anyway.
Okay, so okay, next question. This is from the What is a realistic number for transactions per second in the network after coordicide and long term after sharding? Estimation, of course. Okay.
Well,
So TPS
I
after.
suppose that I'm not really the right person to answer this sort of question.
Okay.
Well, first of all, after sharding, it's theoretically unlimited because the more TPS you have, the more you shard. And in the cluster 0 after coordicide, well, you should better ask Hans or Wolfgang, maybe some tens of thousands, but they are better equipped to answer this.
Yeah, totally. So, okay, I think this is the last one. So, how can
another one?
Yeah, how can a consensus be found when the node is offline for a specific time frame? Do all transactions made with this node need to be reattached, or can consensus be found after connecting again?
If your node is offline, then but it has still transmitted its transactions before going offline, then the network would normally take care of those transactions, so no need to reattach. Now, when the node comes online after being offline, I guess it would have to listen. It would have to download the stuff and to listen to what is going on in the network, to see what are the opinions of the high mana nodes and so on and so forth. But that's basically what would happen in any DLT. If you was offline and you come to the system, you first have to download the stuff and see what's the state of the ledger.
Yeah, totally. Okay, so I'm going to do one last question. I don't know if this is within your scope, but what are let me put it on screen. So what are the biggest challenges in IOTA's path to solve the trilemma? This sounds like an answer.
That trilemma, I mean, you know that I don't like too much that when people use more or less theorems in this way. This trilemma is something that, in general, among 3 possibilities, you can only choose 2, and so on and so forth, right?
Yeah. Okay, so you just.
I mean, I don't consider this to be a really scientific obstacle on our path. And anyway, we are talking about probabilistic consensus, to which these sort of results hardly apply. So we are building a real world system which aims for probabilistic consensus, and we prove that it will work with high probability. And but I just don't see why should we care at all about trilemmas and stuff of this sort. We just build the stuff and show that it works.
Great. Okay, so that's all I have. I don't have more questions. So I just want to thank you, Sergei, for being here today with us. Thanks a lot. It means a lot for us.
Thanks, Karpinch, and thank you everybody who came to see the talk. Thank you.
Okay, so we will meet again next week, guys. And this video will be uploaded to YouTube, of course. So bye. Take care.
Thank you. Take care.